right, let's take a look at some quadratics. First of all, let's look at the graph of a quadratic. So when we look at the graph of the quadratic, we have to recognize that right through the center of the quadratic is the axis of symmetry. On either the left or the right side, we have exactly the same situation. So the axis of symmetry is a very critical part of our quadratic equation. We'll also notice that along that axis of symmetry, we have our vertex. And our vertex is the point. There's many things that we can see about the vertex. It's the point through the axis of symmetry. It's also the point where the curve turns. And so we can use lots of information based on knowing the vertex. We also can see that the vertex in both of these cases are minimums. If the parabola had been turned upside down, it would have given us a maximum value. But both of these are positive parabolas, and so they give us minimum values at the vertex. The vertex is located right on the axis of symmetry. Okay, so now that we've recognized that piece, let's continue on and see what else we can determine from some of this information that we have. Okay, so as we look at the equation of either one of these problems, we can tell that we have the same structure. And the structure of a quadratic equation is a standard form. In this particular case, we're written in standard form, which is the same thing as y equals ax squared plus bx plus c. And we need to know this particular structure so that we can calculate some other things knowing what all of our coefficients are, because we talk about other pieces of our graph using the coefficients of our terms inside this standard form. So remember that the vertex equation, not the vertex equation, but the axis of symmetry equation tells us what x is equal along this axis of symmetry. So that equation is given to us as x equals negative b divided by 2a. So we need to be able to recognize what our a and b is in our basic equation. And so we can simply pick that information off, because when we look at the equation and we line things up, we can see where everything is. And so in both of these equations, we actually have an a that is equal to 1. And having an a that's equal to 1 is very helpful because we don't have to worry about that extra coefficient. Later, we will see different techniques where a is not equal to 1, and we'll have to do some other things. But right now, let's do the simple situation. So we know that a equals 1, and in our first equation, this one right here, we also see that b equals 5. So when we put it into our equation for our axis of symmetry, we end up with x equals negative 5 divided by 2. And we don't have to worry about the a, because remember, a we said was 1. And so 2 times 1 is just 2. So our axis of symmetry in this case is negative 5 halves, which actually is the same thing as negative 2 and 1 half. And if we look at our axis of symmetry right here, we see that it is at negative 2 and 1 half, just like our evaluation told us it was going to be. We can do the same thing over here to this equation, and so when we substitute in our b, and in this case our b is negative 2, so we have negative b, our b is negative 2, and it's all divided by 2a. A again is 1, so we don't have to worry about it because 2 times 1 is just 2. So here we have the fact that our equation says take the negative of our b value, and our b value is negative, so that means we have a positive 2 divided by 2, so x equals 1. And again, we recognize here that our axis of symmetry is along the line of x equals 1. Okay, so now that we have those things figured out, we also can take a look at some other features of these quadratic equations. But let me clean this board up real quick before we go on. Okay, so our axis of symmetry has been rewritten, and now we're just looking at our graphs and our equations. So some of the other features that are really helpful when we're dealing with parabolas is to find out where the parabola crosses our x-axis. We also want to be able to find where our parabola crosses the y-axis. So we're going to look at both of those instances. The more difficult one to deal with is where the parabola crosses the x-axis. So we're going to deal with that first. We have to recognize that the x-axis has a y value of being 0. So when we set y equal to 0, we can rewrite our equation so that 0 equals x squared plus 5x plus 6. Now, we can work a whole bunch of values in here to try to figure out when x equals, or what values of x will make this whole thing equal to 0, or we can use a basic piece of logic that tells us that anything times 0 gives us 0. And it doesn't matter what order we put that in, it's still going to be 0. So if we have 3 times 0, we get 0. If we have 0 times 4, we get 0. Anything times 0 gets us 0. So what we need to find are two factors, one of which we can set to 0 to find the value of x, and then we'll figure out the other factor by setting the other one equal to 0. And we'll see that as we go through this exercise. So we have to recognize that this quadratic equation can be generated from two factors. In this case, we recognize that because our first term is x squared, the only way we can get x squared is to multiply x times x. And remember, this is just the distributive process that we're doing in order to figure out what is inside each factor. Because when we reverse this operation, we should end up with our trinomial, x squared plus 5x plus 6. So we're undoing that particular distribution by recognizing that x times x is the only way to get x squared. We also have to recognize that our last term in our polynomial, in our trinomial, also is a product. It's a product of whatever is here and here. And so we can place some very critical pieces of information in our toolkit so that we can figure out exactly what needs to go in those places. So when we think about a positive product, we should always recognize that the signs of the two factors have to be the same. Because if we had a positive 3 times a positive 2, we're going to get a positive 6. We would get a positive 6 as well if we had a negative 3 times a negative 2. That would give us a positive 6. So we have both instances that's going to give us a positive 6. So we have to use something else to make us recognize which one of these is going to be the one that we're going to use for our problem. So that's where the center term comes into play and its sign. So we recognize that this center term is a positive 5x. Okay, so realize that whatever we put into this spot and this spot, they're going to have to combine to equal this positive 5x term. Well, since they have to become positive in a combination, we have to use the positive values so that we end up with a positive 5. And let's just walk through that to see what I'm talking about. Oops. So we have a positive 3 and a positive 2 in that situation. And when we distribute each of these terms into the other binomial, we end up with x squared is our firsts, so our x times x. And then when we multiply our x times our 2, we get plus 2x. Then we're going to multiply our next term, which is our 3, by x, and we get plus 3x. And then we're going to distribute that 3 to the 2, and we get plus 6. So we've distributed each term of the first binomial into each term of the second binomial one at a time, and we end up with this polynomial. Well, we recognize that these are like terms, so we can combine those, and we get x squared plus 5x plus 6. And because that is true, because we can say that, then we know that we have to use the positive values in order to get our 6 and not the negative values. Let's just double check by using that example so that we can prove to ourselves that that is the case. So we're going to start over again with x and x. And this time we're going to substitute -3 and -2. Now we already know that that's going to give us a positive 6, and we already know that x times x is going to give us an x squared. So we know that we have those two things already established. What we don't know is what's going to happen in the middle here. So when we distribute this -3 to the x, we get a -3x. When we distribute this -2 to the x, we get a -2x. When we combine those two terms, we get a -5x. And so this all ends up being x squared minus 5x plus 6, which is not what we want. We want positive 5x in the center, hence we must use this solution set as our new factors, as a recreation of our original equation. So now that we know that, I'm going to clean up this mess, and we'll just finish very quickly to show how that then becomes our points on our graph. Okay, so our two factors we said was x plus 2 and x plus 3, and they both, all this thing has to equal 0 because we're looking to see where the graph crosses the x-axis, and so y is 0 where this graph crosses the x-axis. So as we said before, when we multiply 3 times 0, we get 0. When we multiply 0 times 4, we get 0. So anything multiplied by 0 gets us 0. So that means if we make that equal to 0, 0 times x plus 3 is going to be 0. If we make the other term 0, then the other factor 0, we have x plus 2 times 0, and that equals 0. So because of that, we're able to now establish the fact that x plus 2 can be set equal to 0, and we can find a value of x. And notice that when we do the math, we have x equals -2, which is exactly what we have on our graph. When we do the other factor and set it equal to 0, and we solve for x, we have x equals -3. And if I cleared up all this mess, you would see that it crossed at -3 as well. And that's how we get our zeros, or our x-intercepts, or our solutions, or our roots, because those four terms all mean the same thing. Roots, zeros, solutions, and x-intercepts are all solved the exact same way. So I solved this second problem so that you could see the solution and see that it does indeed graph. The big difference between this one and the previous one is that we have a -3, so that means we have to have one sign negative and the other sign positive in order to multiply together to get a negative product.